Welcome, everyone. Thanks for joining us and being here today, and by choosing this session over all the 7 ongoing ones. And my name is Shaowei, and along with my colleague Mia, we are very excited to share our story of integrating Ray at Airbnb. And in today's session, we'll use Llama Fine Tuning as a specific case study to share our story over the next 30 minutes. And this is a high-level agenda of what we will go over today. First of all, I will be sharing an overview of how we integrate Ray as the foundation ML compute layer. And after that, I will be introducing a few open source frameworks that we adopted to enhance the Ray fine-tuning ecosystem. And with that, I will pass over to Mia to share one specific LLM fine-tuning use case based on text summarization. And in the end, we will open the floor for a quick Q&A session before we close today's topic. And now, without further ado, let's dive into the infrastructure overview prior to the Ray integration. And we shared this stacked graph last year in the Ray Summit 2023. And so it basically have 2 highlights. On the one side, it's very Kubernetes-centric. Computing for at Airbnb is primarily built on top of Kubernetes, hence the ML infrastructure and the related application and the services. And you can see all those are deployed as native Kubernetes deployments, services, and pods. And on the other side, it's very operational support burden heavy. And, as you know, like ML deployments often require special handling. For example, for distributed training, you would require dense scheduling. For model online serving, you like to have a fractional GPU supported to have a higher GPU utilization rate. Whereas the internal Kubernetes cluster is primarily designed for long-running microservices. So those features are not widely supported. And in this design scheme, ML ops, in essence, is Kubernetes ops. We are in the loop of co-managing the entire Kubernetes cluster with another infrastructure team. So this not only introduces a lead abstraction between the 2 teams when we do feature planning, operational support, but also introduce a feature gap between vanilla Kubernetes ecosystem and the ML applications that has to be filled in by the infrastructure team. To overcome those challenges, we've adopted the Ray AI runtime at the ML development layer. That is to enable the end user to use retrain Ray data directly due to the LLM model development process. And that our strategy, including the deployment of KubeRay, which as the central orchestrator to manage the Ray clusters, as well as the Ray job CR. It's a customer resource definition that helps us to manage the life cycle of each individual job. And we are using 1 job per cluster mode in this approach. And for the end users, Infra team offers 2 sets of APIs. The first set is based on ad hoc job submission. So user can wrap a local developed full-fledged Ray application and submit it to remote Ray cluster for ad hoc execution with the configurable hardware like resource and requests. And on the other side, it's a workflow DSL-based interface. It's based on Python decorator that allow user to easily decorate their existing Python workloads and then translate into heavy lifting Ray computation that can be embedded into their existing ML production workflows. Now let's switch gear for a moment and move on to the fine-tuning infra that we build on top of this compute layer. It contains several functional layers that were roughly divided into 3 categories. The first category is for the application level. It's a direct user-facing that allow ML practitioner to access the foundation models. And the second layer is on the cluster orchestration level, which maintains the efficient scheduling of those workloads being scheduled to the GPU cluster. And the third layer is what we call the compute optimization layer. It's primarily focused on maximize the GPU utilization rate. And building on that idea, let's take a closer look at each layer and the goal that we're optimizing on. For the fine-tuning application layer, it's basically to make the access to open source model as simple as possible. And compared to the traditional ML development process that require model owner to write neural network layers using TensorFlow or PyTorch, fine-tuning app oftentimes operate on a higher level abstraction with the configurable steps starting from choosing the foundation model, the post-training alignment techniques, and then opting for like resource optimization techniques like LoRa or quantized LoRa. And as you can imagine, like with more and more app developed here, the next layer is to make sure those fine-tuning apps that created can be efficiently scheduled. And from the service access point, those computer resources can be accessed by the job and the workflow APIs. And then upon the mission, there is a central computer job scheduler that will schedule and manage those workloads based on different prioritization rules. And the actual RAID computer cluster will be materialized upon scheduling. So based on the application and how we schedule those, just as important is the last functional goal to make sure that all the reserved GPU capacity can be fully utilized. Here on the software side, we maintain the Amazon machine image and the Docker containers to keep up to date with the latest NVIDIA drivers and the Python packages. And on the hardware side, within each P4 host, A100 GPUs are connected by NVLink links. And across multiple P4 hosts, we use the AWS Elastic Fabric adapter to achieve GPU direct RDMA. This is to address the network throughput constraints for common like seen for the distributed training based on model and data parallelism. And so once we launch this platform, there are a couple of challenges we're facing similar to you heard from the other talks. The first one is the first challenge actually lies in the fact that the community are growing rapidly fast. We're seeing like new foundation model, new alignment techniques developed on like monthly or even weekly basis. And initially, we started with a set of fine-tuning scripts for like Llama, for Flan T5, but does not scale well with the velocity of the cloud community growth. And the second challenge is on the related node is around how the scarce GPU under reservation. Those are like A100s we pay $720 for, regardless we use those or not, and how to make sure those can be allocated properly. And we need a balance between static allocation for high SLA jobs and a dynamic allocation for teams with the like, prototypes and ad hoc usage. And the last challenge is around the dev efficiency. So we want to make sure that model can be retrained on the fixed cadence, and those like retraining process can also be shared across different use cases and different teams. So based on those challenges, Infra team started the integration with both open source and in-house built solutions that I'm going to share. And the first integration point is around a open source framework called Llama Factory. It's a popular project on GitHub today with around like 30K stars. And with the help from Llama Factory, it unlocks more than 100 base models with access to various alignment techniques like supervised fine tuning and commonly used RL techniques. And in the meanwhile, the framework offers unified data templates, meaning that the user can switch to different foundation models easily without changing like the interface at all. And last but not least, if you check the code on the right side, you can embed with the retrain framework seamlessly. In each training loop, you can just import the fine-tuning modules from the framework, and then use a torch trainer to orchestrate distributed GPU workers to start the fine-tuning workload efficiently. And next part is another open source framework called Kueue. It's a Kubernetes native system that abstracts the way how to define resources and how different jobs can consume them. If you were here in the last session, it's very similar to the unicorn that Apple team adopted with a lot of feature parodies. And so the most importantly, Kueue, when we made the decision was it has a native integration with the Kubernetes. In other words, it understands how Kubernetes defines the resource. It understands the RAID cluster and the RAID job resources. And here, by abstracting away the resource types that are the A100 GPUs into guaranteed resource queues, those highlighted by the blue color, so production job can get a predictable SLAs to access these queues. And on the other side, for ad hoc jobs like the prototypes and evaluations, user can submit to the preemptive queue, those highlighted by the yellow color, where it will be one-to-one map to the guaranteed queue size, and then sharding to multiple shards with the fair sharing guaranteed across different preemptive queues. And from the user perspective, a job can run into up for retry state if preempted, but it will run into success or fail in the end eventually. And on the last note, that Kueue also offer a simple Prometheus and Grafana integration so that the infrastructure team can monitor those two metrics to decide on the overall cluster allocation and the reservation. For example, if the number of pending jobs is higher than a certain threshold, then we decide to scale up the cluster. And if the certain team-based cluster queue utilization is low, then we scale down the cluster accordingly to save the reserved instance cost. And another change around the integration is between Ray and our in-house workflow engine. Here is we introduce a framework called the GLOW, short for Generalized Language Offline Workflow. It basically standardizes and offers reusable components for data preparation, fine-tuning, batch inference, and evaluations. And take the batch inference as example here. Workflow will be submitted through the central workflow API. And then we use Kueue to launch the ephemeral Ray cluster that takes care of the data sharding, worker provisioning, and data serialization via Ray data. And within the yellow box, user can choose two different Ray actor-based engines for the batch inference, including VLM, TRTLM, or like a remote service call to like a vendor-based APIs. And this unified API makes it easy to switch between in-house developed model and vendor-based closed source models. And building on the idea of easy sharing, the entire workflow can also be serialized into a TOMO config for code review and publish. Before we proceed, let me recap on the changes we introduced to address those challenges. Llama Factory and its widely support for open source model keep the community up to date with the open source world. And the Kueue-based native integration with the Kueue can help us to maintain a high allocation rate for the entire GPU clusters. And lastly, by integrating a generalized LLM workflow, so it makes it easy for new users and different teams to share their LLM-related production workflow. In the next part, I will hand off to my colleague Mia, and she will use one fine-tuning use case to show how these changes help improve her day-to-day LLM development experience.
Thanks, Shaowei. Now, I'm going you through a concrete fine-tuning examples. Of course, in Airbnb, there are many fine-tuning cases. The purpose here is we will go through one fine-tuning exactly applications to tell us what is the life cycle of the fine-tunings, how Ray cluster and infra setup can help in this process. The specific case we're going to go through is a text summarization cases. My talk will become three parts: is why we choose fine-tunings from product perspectives, how the supervised fine-tuning perform on the initial model stage, and how we leverage reinforcement learnings to continue that smaller model to grow. Why fine-tunings? Of course, there are a lot of reasons why we choose fine-tunings. This is a typical cycle of why we choose the fine-tuning. For example, in a summarization cases, we will start let human to establish a baseline to say, okay, we have one group of humans write the summarizations, another group of humans to evaluate the quality score of their summarizations, and also the time spending on those summarizations. This becomes our product baselines in terms of applications. Whether we can leverage a large language model in any of the applications, that's kind of one of the baselines. Once we have the baselines, now we are trying to see, okay, how mature the large language model community is. What is one of the best models in the market that can achieve the human level of the performances? This has been done through examples. Here is a GPT-4. Of course, there's other up-to-date open source models that can give us some of the baselines to say, okay, has a large language model been mature enough to capture the human level of the performance in terms of the productions? What are the relative improvements from the human baselines, and what is the latency can be achieved? after this stage, the next stage comes the question is, can we even optimize more through fine-tuning process? The example here is probably a while ago, we were able to even use 11 billion T5 models through a series of the fine-tunings and improve a performance both exceed the human level and GPT-4 levels, of course with a better customized latency. To summarize, why we fine-tunings, first, we want to get a better latency, better management cost, and we believe the performance can grow with time goes by. This is a very simple process to see how we illustrate the supervised fine-tuning in the initial state. In this stage, the main demand from the infra perspective is experimentations. I think one of the challenges Shaowei mentioned is there is a ton of the open source model communities that came out every week. There's new models that we want to do experimentations. How we have that? So we were able to leverage preemptive queues. Those are usually ad hoc experiments. Sometimes it's run very long, sometimes very short experience. But the goal is here, now we have a human-written examples with some of the high-quality AI assistant labeling, then we can achieve a fine-tuning, supervised fine-tuning process against mostly widely available open-source community models. After we have initial model performances, this is just the start, right? So we want the fine-tuning. Another major benefits of the fine-tuning is we hope the model to grow along with the application development. So now I'm going to go through how we have the reinforcement learning in place to let this smaller model continue to improve its performance. As you can see, the first step we have here is to collect human feedback. As the model integrates with the applications, we often get some feedbacks from humans. Some simple feedback like sum up, sum down. Sometimes we get criticized feedback from humans about the models. This mix on how we prepare the data from just the sum up, sum down to a pairwise of the training data, right? Some of the technique we were using like chain of density, this is when human just like a sum up, sum down, but we have some guidelines to say what is a good summarization going to be? What is the key performance of that summarization going to be? So through that iterations prompting technique, we can collect some of the pairwise training data through ask a model to rewrite it for X times according to our guidelines. This is another interesting prompt techniques used in this particular example, which of course is gathered from Anthropic AI. So when we integrate with the product, we often get negative feedbacks from humans, say, okay, this part isn't summarized well, this part needs improvement. Through continuous critique feedbacks, we can also collect pairwise preference through human, through that alignment process. Now passing to getting the data, having the human feedback in the loop as first steps. The next step is how we do the model alignment. So in this example, we have been done model alignments, both through human in the loop preference data set or through the virtual judge. We see both of the performance has been gained a lot from the initial model baselines. So this is a sample we use. Of course, with the open source, I think Shaowei mentioned, we were able to align with different type of the alignment strategy, not only to DPO, PPO, including like a KTO, IPO, ORPO, simple PO. So there's a lot of things we try, and in this particular cases, we tried the DPO, which we particularly feel it works pretty well for summarization tasks, both from engineering resource efficiency and also from the computing efficiency. Also, in the performance-wise, we find it exceed PPO as well. But in other cases, it might subject to the user cases. After fine-tuning process through this framework, Then we will have the last piece, which Shaowei mentioned about, is how we do batch inferences and how we make that model circle back to the applications. So the batch inferences we have here is an internal framework we build, which both integrate with a human in the loop for the evaluation and also virtual judge systems. So a lot of generative AIs, there's no ground truth tied to it. One of the challenges is how we make the evaluation more sound whenever we release the next version of the model. Combining with human, align with a list of the virtual judges, help us do a stage-based evaluations and making sure the model iteration release capture those. This is a entire cycle for this specific summarization cases. Once the initial model gets fine-tuned, we are not stopping it. We start to collect the human feedback starting from sum up, sum down, leverage a lot of prompting technique and data alignment strategies and to continue to improve the models. So this is how these examples might map to the ray train. First of all, we were able to get a lot of experiment done in the initial model stage to quantify hundreds of the experiments can be done in a few days of the time frame. And through the initial model training, we were able to achieve a relative smaller data set with comparable performance. Last but not least, the growing infrastructures did help us to schedule the job to have the model re-fine-tuned and realigned with the human preference on a periodic basis. This significantly reduced engineering effort in terms of maintaining those models and keep monitor those models. Now I'm going to pass to Shaowei to talk about key takeaways.
Thank you, Mia. Yeah, just a few highlights to conclude today's talk. The first one is around the Ray and its open source ecosystem. So it's not about only Ray train and Ray data. We're seeing a growing ephemeral related projects around the Ray. For example, Kueue and the Unicorn. Those are built for you to easily schedule your Ray workloads. And all those open source frameworks together laid a solid foundation for us to continue work on the Ray-based compute layer. And the second part is specific around the fine-tuning. We're seeing that in-house fine-tuned smaller model actually outperform the model, larger vendor-based closed source models in specific business use cases. And the third one is we think Llama fine-tuning and alignment is a continuing process, and it will take iterative efforts to make the system more performant. And looking ahead, so what we shared today is just a small model we started last year, and we're working on more complicated use cases today with a RAG-based system with multi-agents and multi-modality models as well. Hopefully, we can share in the future maybe in the next summit as well. Thank you.
All right, thank you, Shaowei and Mia. I think we have time for a few questions. So if you raise your hands, I can pass the mic to you.
How difficult was it to move away from Spark to more Ray-based system? Are there still some workflows which you feel like are stuck over there?
Yeah, that's a good question. So for Spark, we primarily use for two use cases. The first one is access to data warehouse, which I believe today is still the most efficient way to do because we don't have a good story from a Ray cluster to access Hive tables. And on the other side, the other usage for Spark is batch inference. You can think that each executor will load the model. We have a Python kernel running in Python, PySpark executor for the inference. And all those use cases will be replaced by Ray data and mostly done on our side. Yep.
Yeah, hi. So you had a slide for right here. You had a slide for after you started using Ray, and I still saw you had Harvard in there. So why can't you use like Ray's distributed training abilities instead of using Harvard?
Yeah, that's another good question. So we run Harvard with the Kubeflow prior to Ray integration. We use basically the MPL operator to orchestrate the group of pods. And with the Ray, we can basically reuse the Harvard trainer to replace that functionality. That's doable. We're not seeing any downsides for doing that. The main blocker right now is we have this data pipeline customized for TF records loading, but we're seeing some support drawback on the Ray data side if you're familiar with Ray data with TF records. Yeah.
Any more questions? All right, thanks again, Shaowei and Mia, and thank you everyone for coming. Enjoy the rest of your Ray Summit.